4.6 is looking at some applications using exponentials and logarithms. So you'll notice that here in the first example, we have this function that models the amount of a bacteria present after t minutes. So you should recognize this is really just the PERT formula. Okay, it's just that I'm modeling something other than money here. So you'll also notice that with the investment problems, we were working with annual interest rates, so our time units were years. So in this case, we actually have other time units, but those are just given in the problem statement. So other than that, I mean, we can answer these questions pretty much just like we did with the investment problem. So what is the initial amount? So I can actually read that off. Or if I wanted to, well, initial would imply time is 0. So I could plug in 0 for t. And so indeed, I get my 2,000 grams. Remember the growth rate I can also read off. So that looks like 0.03. Remember we give that as a percentage. And then I have to put some units on this. So let's see, this is growing. This is grams per minute. So this is growing by 3% grams per minute. Okay, how much is there in 10 minutes? That's just the amount after 10 minutes. So if the calculation's simple enough to do it in my head, I'll go ahead and do it. And then this is the amount after 10 minutes, so this would be in grams. When will there be 3,000 grams? So now I'd actually be setting the whole equation equal to 3,000. And so I'd have 3,000 equals 2,000 e to the 0.03t. My goal is to solve for t. Remember, first I have to isolate the exponential. So I would divide by that 2,000, then change to log form. So it's the exponent is the ln of the other side, and then divide. And then I have to put units, so this would be time, so in minutes. The population of bunnies in a sanctuary obeys the law of uninhibited exponential growth. So actually what that tells me is that tells me that I can model this using the PERT formula. There are 12 bunnies initially. Put that in. Well, let's see. Let's add something to this. The population of bunnies obeys the law of uninhibited exponential growth. There are 12 bunnies initially and 16 after 2 months. Let's ask something. How many are there in 5 months, say? So my goal will really be to answer that question then. how many are there in 5 months? So my goal would really be to plug in 5. But the thing is, I don't know the rate yet. So generally speaking, with this type, oh, I have that written down here. I see. Generally speaking, for this type of problem, the first thing I have to do is get the rate. Okay, so to get the rate, I need a pair. And so you see how here there are 12 initially. Let's see, we counted for that. What else does it say? There are 16 after 2 months. So that's the pair I'm going to use to get the rate. So there are 16 bunnies after time 2 months. Now I can solve for R. So what is that? 4/3? So the rate is ln 4/3 over 2. Next, I'm going to see if I can build a general function to model this population. Okay, so what I'm going to do there is I'm going to take this rate and I'm going to plug it in here. So that's what that looks like. Now, remember I have that rule that says I can cancel if I had e to the ln of 5, say, I can cancel that e with the ln and end up with just 5. So I'd like to try to simplify this. It's just that I actually have to rearrange this because I need the ln next to the e here. So what would that leave me with on the outside? It would leave me with a t in the top and a 2 in the bottom. I mean, think about this. I have power to a power here, so I would multiply these straight across. So wouldn't I have something like that? That's what I had up here, right? So we'll do several of these and you'll see, I mean, there's a pattern with simplifying these. So you just rearrange so that the ln is next to the e. Move the remaining items outside as a fraction. That way I can then cancel and my base drops. So there's my general function. Okay, now what was my question? How many are there in 5 months? So now I can answer this question about 5 months. Okay, so I plug 5 in my general function. Okay, so that would be the number of bunnies, the amount of bunnies in 5 months. When will there be 17 bunnies? So now I have to take my general function and set that equal to 17. Okay, I always want to isolate the exponential first. So I'll divide by 12. Now this one, since I have a base other than e, ultimately I'd like to be able to enter this into a calculator should I want to. So what I'm going to do here is I'm actually going to take the ln of both sides. So once I have that ln, that logarithm, I can then move that exponent down. Okay. Then to solve for t, let's see, I guess I need to multiply up the 2. Okay, and then divide by ln 4/3. And then my time units were months. Okay, a radioactive material decays according to the given function. So the difference you'll notice right away with this one is that I have a negative in that exponent. So that tells me that this material is decaying rather than growing. Okay, it's getting smaller. But I can do the algebra the same way. So what is the decay rate? So again, I'm looking at the R here. So the only thing is when I give that decay rate, I actually give that as a positive number. Let's see, so what is this? This would be milligrams per hour. But I go ahead and give that as a positive number because when I indicate that this is a decay rate, that means that if I were to substitute that back in the formula, it would have that negative in front of it. How much is left after 9 hours? So that would be amount in 9 hours. Like so. Okay, now something like this. I don't know that number in my head. I would leave it as it is. That'd be my test answer. When will 70 milligrams remain? Let's see. Make sure I put units on that. So I set the whole formula to 70. Solve for t. Divide by 100. Change to log form, so the exponent is the ln of the other side. Equals to my t. And divide. So actually you'll see it kind of looks like I have a negative number for t here. But actually I don't, because actually ln of 0.7 is actually negative. So I actually have a negative over a negative. So the result is actually positive value of time, which is what I needed. What's the half-life? So I need a little definition. So half-life, this is the time it takes for half of the substance to decay. Okay, so the question is, how long will it take for half of the substance here to decay? So if you look back up here, let's see, what was the initial amount? That was 100. So actually then, I would be interested in knowing when will that 100 milligrams decay to 50 milligrams. Now, actually I don't need the initial amount here, because actually look, this is kind of interesting. If I know the initial amount is P, if I'm looking for the half-life, I'm looking to know when will I have half of P. Okay, so I cancel the P's anyway. Okay, so I divide by 100, so I have a half e to the negative 0.87t. Same thing over here, right? This would be a half is e to the negative 0.87t. Okay, so I don't actually need to know the initial amount. Change to log form. Okay, and then my time units, what was that, hours? And again, this is a positive value of t, because ln of a half is actually a negative number. Okay. This guy says the half-life of a substance is 240 years. 50 grams are present now. How many grams will be left in 600 years? So again, we start out with the PERT formula. Okay, we have 50 grams present now. So we're thinking of time starting now. So we're going to use 50 for our initial amount. And then again, the question is really, can I plug in the 600? But again, I don't know the rate yet. So before I can answer that question, as usual with this type of problem, I have to get the rate. Okay. So then let me see what I know. Well, I know the half-life is 240 years. Okay, so let me see. That means if I start with 50, I'll end up with 25. That takes 240 years. So again, I don't even need to know the initial amount here, because when I divide, I'll always arrive with that half on the left side. Change to log form. Divide, and I have my rate. So then the next step is to build the general function. So how I would do that is I would take the rate and plug that in here. So I'd have 50 e to the ln half over 40t. Rearrange. So the ln's next to the e, the t over 40 is on the outside. So I can then cancel, base drops. Okay, and there's my general function. And now I can answer the question, how much will be left in 600 years? So I'm going to plug 600 in. I lost a 2 somewhere. Did you catch that? So look, R is 240. So let's fix that. Just noticed I lost my 2's. Okay, so I'm plugging in the 600. 50 times a half, 600 over 240. So there's an answer. I should try to simplify that. So let's see. That'd be what, 60 over 24, divide by 6, 10 over 4, 5 over 2, reducing. And then what are the units? Grams. So in 600 years, there's my total number of grams. Okay, now notice I can never actually multiply like the 50 and the 1/2 and make this. No, right? Because the 1/2 is under the exponent, the 50 is not. So I could not do that. A mummy is discovered to contain 21% of the carbon-14 it initially did. The half-life of carbon-14 is 5,730 years. How long ago was the mummy buried? So I could actually really rephrase this question. It's really asking something like, how long does it take for the initial, so 100% of carbon-14 to decay to 21%? That's really the question here. So I'll start with my PERT model. Again, first step is going to be get the rate. I'm going to use the half-life to get the rate. Okay, so I know whatever I start with, I'm going to end up with half of that. And the time is 5730 years. Cancel the p's. Change to log form. And divide. And after I have my rate, I'm going to build the general function. Okay, so I'm going to take my rate, put that in here. Now notice here I don't actually know the initial amount, so I have to leave that as a variable p. Rearrange this as usual. Either way, so I did the last one. Then I can cancel, and then I'll be left with this expression. So that's the best I can do without knowing the initial amount. But now I can go back up and answer this question. So now the question is, how long does it take for the initial amount of C14 to reach 21%? So in other words, if I'm starting with P, how long does it take to get to 0.21P? Cancel the P's. Should I be consistent? I'll do 0.5. Doesn't matter. Take the ln of both sides. And bring the exponent down. Okay, multiply this up. And divide by this guy. And then this was in